Hello and welcome to this video for Chemistry 20 in the Science 10 review unit. We are currently going to today review how to write reactions. Now, if you remember back to Science 10, there are 5 main reaction types that we're going to review today. But one thing before we get into that, whenever we're writing reactions, it's very important to know whether, or to include the states, when you're writing a reaction. So states of everything, like I said, depend on, first of all, the substance that you have, what type of compound or element it is. And then secondly, whether or not the reaction is taking place in water or not. Because whether or not the reaction takes place in water can change the state of your compound if it's soluble in the water. So that's what we'll review today. We'll review states and then the reaction types. So first of all, if you have an acid, remember an acid is only an acid and it's only going to have its acid name if the acid compound, the hydrogen compound, has been placed in water. Okay? Not everything that's aqueous is an acid. Aqueous just means it's been dissolved in water. But in order for an acid to have its acid name, it has been dissolved in water. So we know acids are always aqueous. Elements can be solid, liquid, or gas. Remember, the periodic table tells you essentially for the metals, everything's solid except mercury is a liquid, and it tells you that mercury is a liquid in the element box. But the rest of the metals don't tell you what they are because they're all solid. The non-metals in the element box, it'll tell you. Or in Chem 30, you'll have a color-coded data booklet, and the colors, again, there's a key that lets you know what state they are based on their colors. Molecular compounds, remember, are a little more complicated. They can be solid, liquid, or gas. So either it's a common molecular compound in the question, or the question will give you the state to use for the molecular compounds because there's no way to predict it. And then ionic compounds. If your ionic compound is not in water, it's always solid. But if it is in water, you have to use something called the solubility chart to determine if it's going to stay solid because it's insoluble or change to aqueous because it is soluble. Now, the solubility chart only gets used when you have a single replacement or double replacement reaction. Okay, those are the only reaction types that take place in water unless the reaction tells you otherwise. Okay, so you only use the solubility chart, which I'll review in a second, for reactions that are single replacement or double replacements that we'll review today as well. Okay, so here is your solubility chart. It is on the back of your periodic table. And so what information you have, again, an ionic compound. This is the solubility for ionic compounds. You need to find one of the ions in your compound along the header row. Okay? So you'll notice most ions are negatively charged in the header row, but group 1 ions are listed up here and ammonium are listed up here. Group 1 ions are things like sodium, potassium, lithium. They are all in the first column on your periodic table. Those are some of them, not all of them. There's also rubidium, cesium, francium, okay? Rather than listing them all, they just put a blanket statement there, group 1 ions. So you have to know if you have a group 1 ion, you're looking in that column, okay, or ammonium. So once you've established which ion you're starting with in your header group, you then find where it matches in the 2 rows below. Is it either in the middle row, meaning it's very soluble, and therefore it would be aqueous? Or is it only slightly soluble in the bottom row, and for that, that's where we would leave them as being solid? Okay? So if we look at an example, I'm just going to erase that there. So very soluble, again, are our aqueous ones. Slightly soluble are solid. Remember, again, the group 1 ions, the first period or the first column on your periodic table. So I'm starting with sodium acetate. So the 2 ions in that compound are sodium, which is a group 1 ion, and acetate. Acetate is actually right here on the periodic table. On the solubility chart. So when you're doing these questions, once you find one of the ions in the header, like I said, for the first few columns, you're looking at the bottom to see compounds that are insoluble with those ions. If sodium acetate is not in the list below, which it isn't, there's silver and mercury with acetate but not sodium, that means that it fits up here in the middle row instead. Okay, so what this chart is essentially saying is that most ions with acetate are going to be aqueous, with the exception of the following compounds listed below. Okay, so if it's not in the list of things below, that means it fits in the middle row, and therefore that compound is aqueous. Okay, let's look at another example, barium sulfate. Sulfate, again, is up here. Like I said, you're usually finding the second ion, the negative ion, or the anion in the compound on the header chart. Again, I'm looking at ions that would be insoluble with sulfates, and if it's not in that list, it's in the middle row. But barium is in this list of things that are insoluble with sulfate. So that means barium sulfate is solid. Okay? Potassium hydroxide. My hydroxide is right there. For the last three columns, most ions are insoluble or solid with the last three column ions, with the exception of group 1 ions and a few other examples, and ammonium and some other examples there. Okay? So my question now is, with my hydroxide, do I have a group 1 ion bonded to it? And potassium is a group 1 ion, right? Check the first column on the periodic table. Potassium is in there. So that means, again, if it's in the middle, it's aqueous. So potassium hydroxide is aqueous. Okay? Hopefully now you're kind of getting a feel again for how to use this. Next I have lead nitrate, and lead is multivalent. Remember, if a metal is multivalent, it can actually affect its solubility on the solubility chart. Now with nitrate, there are no leads that are solid with nitrate. So that means no matter what charge it has, it's aqueous. Okay? But some of them, like the next example here, mercury acetate. Acetate is up here, and there is a mercury with acetate listed down here. But when there are two ions of mercury, and here there's only one ion of mercury, that's because, again, mercury is multivalent. So it is not that compound, which means that this is actually going to be aqueous. Okay? So if it's a multivalent metal, you have to double check which charge it has to know whether it's solid or aqueous. Okay? Give the next few a try. Pause the video, see if you can give the next few a try, and then I'll put up the answers. So for number 6, we have calcium carbonate. Carbonate is up here. Calcium is not a group 1 ion or ammonium, so therefore it would fit in the bottom and be solid. Iron sulfates. Now, iron again is multivalent. I check with sulfate. Iron, no matter what charge it has, is not listed down there, so it would be aqueous. Ammonium sulfate. Ammonium is here. That was ammonium sulfide. I think I called that wrong. When you're using the solubility chart, again, you're usually finding the negative ion at the top, but sulfide is not up here, okay? But ammonium is. So remember, there are a couple of the first ions that are found on this chart in the header, the group 1 ions and ammonium. So ammonium with sulfide is not in the list of compounds that are insoluble, so it would be aqueous. Now, this example next, lead with sulfate. Sulfate is up here, but I need to know what charge does lead carry, because if it carries a 2+ charge in that compound, it's going to be solid. But if it carries a 4+ charge, it is not. Okay? So remember, for finding ion charges, you look at what they're bonded to. It's bonded to 2 sulfates. Each sulfate is -2, so that means my lead is the 4+ lead in this compound, which means it fits up here and it's aqueous. Okay, So remember again, when you have multivalent metals, you do have to check their ion charge. And then last, calcium phosphate. So I have my phosphate up here. Calcium is not a group 1 ion or ammonium, so it fits in the bottom and is solid. Okay? So hopefully that's a good review for you for using your solubility chart. Now we're going to get on into chemical reactions. So what are some evidence or observations you can make that a chemical reaction has taken place when you mix things together? There could be a temperature change, so it feels hot or cool. There could be a color change meaning maybe you had two solutions that are colorless and then all of a sudden it turned a bright yellow. A solid precipitate could be produced. Precipitate means you have a solid product. If this is happening in a solution, it's going to turn the solution cloudy because those solid particles are being suspended throughout the solution. If a gas is produced like hydrogen gas or oxygen gas in a solution, that would generate bubbles. So these are some hints that you've actually made new substances, and that's why you have the following observations. Now, in a chemical reaction, they can be, in terms of their energy change, either endothermic or exothermic. If the reaction is endothermic, when you write the reaction, your energy would be a reactant because it's reacting with that energy. It's absorbing that energy. Whereas if it's exothermic, the energy would be a product because energy is being released. So sometimes you'll actually see energy in the reaction, not very commonly, but sometimes you might, and if you do, it's just letting you know if it's endothermic absorbing energy or exothermic releasing energy. Okay? Now, whenever we write our reactions, we also have to make sure we're balancing the reaction. Balancing coefficients are what we use to make sure the number of atoms on each side of the equation are equal. Okay? So as we go through and look at some examples, we'll look at balancing an equation. But essentially, what you're looking at when you're writing a reaction is, let's say I'm forming water. So I have hydrogen gas. Hydrogen gas is diatomic when it's in its atom form, and it's reacting with oxygen gas, which is also diatomic. And I, in that process, let's say, am producing water, which at room temperature is a liquid. Okay? So these, again, are my reactants. Everything on the left-hand side of the arrow are the reactants, and this is my product. Okay? Everything on the right-hand side of the arrow, notice again, it's not an equal sign, it's an arrow that we use to show what is happening in the reaction, what we're starting with, and what we're producing. Okay? Now, I'm going to, for a moment, just draw what's happening in this reaction. I have two atoms of hydrogen bonded to each other, so I'm going to draw them as little purple dots. And it's reacting with two oxygen atoms. I'm going to draw that as two green dots. Okay? And I'm making water. Water has one oxygen atom and two hydrogen atoms. Okay? So what we need to do when we're writing a reaction is making sure the number of these atoms match. If I have two purple on one side, I need two purple on the other side. Same with the green, but notice how I don't. Okay? I only have one green currently on the product side. Now, I can't change how many green atoms are in water. Water is always one oxygen with two hydrogens. All I can do is add multiples of those molecules by putting a balancing coefficient in front of the compound. So that means I'm adding another molecule of water, which gives me another two hydrogens with an oxygen. Now I have two oxygens, but notice how that now gives me four hydrogens, which is fine. I can put a 2 in front of my hydrogen molecule to get another H2 gas molecule, and that now gives me 4 hydrogens to match with the 4 hydrogens on the product side. So my balancing coefficients in front of my hydrogen gas is a 2, which means I'm having 2 of my hydrogen molecules. I can put a 1 or leave it blank in front of my oxygen because I only need 1 molecule of oxygen. And then that gives me 2 molecules of water. Okay, again, this 2, you multiply by everything written after it. So 2 times 2 is 4 hydrogens, 2 times 1 is 2 oxygens. Okay, so the balancing coefficient gets multiplied by everything written after it in that either element or compound. Okay, so let's review our reaction types. The first reaction type we'll review is hydrocarbon combustion, and for short, you can write HC. A hydrocarbon combustion is when you have a compound known as a hydrocarbon, which is made of hydrogen and carbon, and it is burning or it's undergoing combustion. Whenever you're told the word it burns or undergoes combustion, that means it's reacting with the oxygen in the air. And oxygen, again, is always O2 when it's by itself and it's a gas. Now, the nice thing about hydrocarbon combustions is the products are always the same no matter what the hydrocarbon is. It's always producing carbon dioxide gas and water gas or vapor. Okay, you do not have liquid water coming out of a burning scenario unless it's in a closed system, but most of the time it's in open systems and you're going to have water vapor being produced. Okay, so this is the generic formula that you'll see written. C something H something is reacting with O2 to make CO2 and H2O. So let's start with a fairly simple example. Let's say we're told methane burns. Okay, methane burns. So what is methane? Methane is a common molecular compound. It is CH4 and it's a gas. And the fact that it's burning means it's reacting with O2. Now my products, again, I should identify right away this is a hydrocarbon combustion because my CH4 is a hydrocarbon. Reacting with oxygen means it's combustion, hydrocarbon combustion. So my products, no matter what my hydrocarbon are always CO2 and H2O gas. Makes it very easy to predict the products. Okay? Now balancing, I'm going to use a different color just to show the balancing. So again, I'm going to put numbers in front of every substance that I have in my reaction. My methane, my oxygen, my carbon dioxide, and my water vapor. Okay? Now for balancing hydrocarbons, usually balancing, it doesn't matter the order you balance the elements in, but for hydrocarbon combustion, it's easiest if you balance the carbons, then the hydrogens, then the oxygens. Okay? So for example, my carbon, I have 1 carbon in my methane and 1 carbon in my carbon dioxide. So my carbon dioxide is good. I'm just going to put a 1 in front of it for now. I can always use pencil and erase it if I need to change it. Then I go to my methane again. I always start with my hydrocarbon, and it has 4 hydrogens in it, whereas my water currently only has 2. So I'm going to multiply my water by 2, so that 2 times 2 gives me 4 hydrogens to match the 4 hydrogens on my reactant side. Now I add up my oxygens on the product side because I have 2 products that have oxygen. There's 2 oxygens in the carbon dioxide and another 2 from the 2 waters, right? Each water has 1, but there's 2 waters. So I have 4 oxygens on my product side. I go back to my reactant side. I currently only have 2. So if I put a 2 in front of here, 2 times 2 is going to give me 4 to match the 4 on my product side. Okay? And then whenever you're done balancing, if you don't need a coefficient in front of something, you can either put it as a 1 or leave it as blank. But that's essentially now our balanced hydrocarbon combustion. Now, when you're balancing hydrocarbon combustion, sometimes you get into situations where you have an odd number of oxygen on the product side. Let's look at what we do when that happens. So let's say we have ethane burning, C2H6. So again, my product is going to be, my reactant is going to be oxygen, And my products, again, are just carbon dioxide and water vapor. No matter what the hydrocarbon is, those are always your products in a hydrocarbon combustion. Now for balancing. I used red last time. We'll use red again. I have 2 carbons in my ethane. So I'm going to put a 2 in front of my carbon dioxide to also have 2 carbons. I have 6 hydrogens in my ethane and only 2 in my water. So 3 times 2 will give me the 6 to match on both sides. Now I count up my oxygens. I have 2 times 2 for carbon dioxide, so that's 4, plus 3 in the 3 waters. Each water has 1, so 3 times 1 is 3. So that gives me 7. That's an odd number, right? So what times 2 is going to give me 7? And in fact, in Chem 20 and Chem 30, it's fine to write a decimal for your balancing coefficient if you need to. So 3.5, and then I put a 1 in front of here. I could also write the 3.5 as a fraction, which you'll commonly see in Chem 30, as 7 over 2. 7 over 2 times 2 would have given me the 7 to match on each side. Okay? Now, if you don't like seeing fractions, or let's say you're given a question where it asks you to record your balancing coefficients in the simplest whole numbers, what you do to fix it, now that it's balanced, is just double everything. So this 1 would become a 2, the 7 over 2 would become a 7, the 2 would become a 4, and the 3 would become a 6. Now it's still balanced, but with the lowest whole numbers. Generally speaking, that's the rules for balancing. You want to use the lowest whole numbers. But like I said, in Chem 30, you're actually going to see some reactions where you're given fractions and decimals. So seeing that at this level is not a bad idea if you want to get into that habit. Like I said, that's not something that I don't allow. I always allow that. Okay? So that is our first reaction, hydrocarbon combustion. Next, we'll look at composition, sometimes called simple composition, also sometimes called formation. These reactions are usually exothermic because compounds want to form. And when something wants to form, it releases energy in that process. Okay? What's happening here are elements are combining to make a compound. Now this reaction is not happening in water, which means I do not use my solubility chart for this reaction. You might want to make a note for yourself. Do not use solubility chart. The only time we'll use the solubility chart, solubility, I want to make sure I spell that right. The only time we use the solubility chart is for single and double replacement reactions, not for composition and decomposition, which is the opposite of composition. So this example I can give you, we have elements combining to make a compound, and depending on what the elements are, we can either make an ionic compound or a molecular compound. Okay? Let's say I tell you magnesium burns. Okay? I'm using that word burns again. This doesn't mean it's a hydrocarbon combustion. The word burns just means it's reacting with oxygen. What's reacting with oxygen in this case is not a hydrocarbon, so it's not a hydrocarbon combustion. It is composition. I have my element magnesium, which is a metal, reacting with my element oxygen, which is O2 when it's by itself, and a gas. Now the compound I'm going to make is magnesium oxide. So my elements combine to make a compound in composition reactions. Magnesium oxide is an ionic compound because of the metal. So when I write the formula of my product, it doesn't matter how many magnesiums and oxygens are on the reactant side, I have to balance my ion charges. Magnesium oxide is always 1 magnesium with 1 oxygen because of their ion charges. Okay? And because this reaction is not in water, I am not using my solubility charts. it is ionic, and ionic compounds are always solid when they're not in water. Okay? Now, the fact that my oxygens are unbalanced, I fix that with my balancing coefficients, right? I have 2 oxygens on my reactant side and only 1 on my product side. So I need 2 magnesium oxides to form. That gives me 2 magnesiums, so I put a 2 in front of my magnesium, and then I'm balanced. I can either put a 1 or leave it blank in front of my oxygen. Okay? So that is a simple composition or formation reaction. Decomp is the same, just opposite. Decomp reactions, you usually have to add energy to make them happen. And here your compound is splitting into elements. Again, I do not use the solubility chart for these reactions because this reaction solubility is not happening in water. Okay, so if the compound is ionic, it's just solid. If it's molecular, on the other hand, it can be solid, liquid, or gas. So let's look at water decomposing. And again, some of these questions can say water decomposes under electrolysis. Fancy words added doesn't change anything. The fact is that we have water, and it's the only reactant. In a decomposition, you only have 1 reactant, and it's going to split into its elements. Again, when we're splitting it into its elements, it doesn't matter how many of each atom are in the molecule. I need to write their formula for how they exist when they're by themselves. So hydrogen by itself is always H2 gas, and oxygen by itself is always O2 gas. Okay, so regardless of the fact that there's only 1 oxygen on my reactant side, on my product side there needs to be 2 to start. Balancing coefficients will overcome that. Okay, so my balancing coefficients now, like I said, there's 2 oxygens, so I need 2 waters to give me 2 oxygens, but that also gives me 4 hydrogens. So if I put a 2 in front of my hydrogen, that will give me 4 hydrogens, and now everything's balanced. Okay, I can put a 1 there or leave it blank. So that is decomposition. Okay, next we will start our reactions that do take place in water. In a single replacement reaction, you are going to use your solubility charts for the ionic compounds, not the elements, just the ionic compounds. Okay, you're going to use the solubility chart. So let's say, now, single replacement actually, what happens in terms of there's a switching of partners? What switches depends on the element you have. So we're going to look at a couple of examples. Let's say I have a metal, I'll call it metal 1, and it is the element by itself, and it is reacting with an ionic compound. Ionic compounds, this should say ionic compounds. Ionic compounds are always a metal bonded to a nonmetal or a polyatomic ion. Okay? Or the ionic compounds can also be an acid, which the H is acting as a metal, such as HCl, for example. The ionic compounds can actually also be water. Water, to a very small extent, is made of hydrogen and hydroxide ions. So the hydrogen, again, would be the metal that I am going to switch with the metal element by itself. Okay, so you might see me write water as HOH, and that's why, because it's made of hydrogen hydroxide to a small extent in a reaction such as single or double replacement. So if my element is a metal, I switch the metals, and metal 2 is by itself, and metal 1 now bonds with the nonmetal. That's a 1, not an I, sorry. Okay, so let's say we have copper metal being placed in a solution of silver nitrate. Now, silver nitrate, again, is ionic, so I have to balance my ion charges. And I have to check my solubility chart. A hint, anytime you have nitrate or a group 1 ion or ammonium ion, those are always aqueous. Okay, so kind of a hint. So what I'm going to do, because my element by itself is copper. My copper and my silver are going to switch. So my silver is going to end up by itself, and my copper is going to bond to the nitrate. Now, copper is multivalent, so how do I know which charge to use in my product? If it doesn't tell you which charge to use, you always use the first one listed on the periodic table, as that is more common. So for copper, that is copper with a 2+. Okay, so it would be CuNO3 2 to make that balance, ion charges. Now, when you have a polyatomic ion like nitrate, I treat it as one whole thing for balancing. So I have 2 nitrates on my product side and only 1 nitrate on my reactant side. There's no brackets with a number after it. So I'm going to put a 2 in front of my silver nitrate to get 2 nitrates. That also gives me 2 silvers, so I'm going to put a 2 there. And then, again, my reaction is balanced. I can put 1s or leave it blank in front of the coppers. Okay, now that is, again, if your element is a metal. But what if your element by itself is a non-metal? So let's say I have non-metal 1 reacting with my ionic compound. This time, what's going to happen is the non-metal is going to switch with the non-metal, the second element in the compound. And non-metal 2 will be by itself, and the metal will now be with non-metal 1. Okay? So for example, let's say you're told fluorine gas, which is diatomic, is bubbled, so it just means it's a gas, so they're putting it in the solution, of sodium chloride. Check my solubility chart, that is aqueous. Okay, sodium has a 1+, chloride has a -1, so that's my proper formula for sodium chloride. So this time, like I said, my fluorine is not switching with the sodium. My fluorine is switching with the chlorine. Okay, so the chlorine will be by itself, which is diatomic by itself. And when sodium bonds to fluoride to balance their ion charges, I have 1 sodium with 1 fluoride. Okay? Again, you check your solubility chart. You see that that's soluble. And now I can balance my reaction, putting a 2 in front of my sodium chloride and a 2 in front of my sodium fluoride to make those elements balance. Okay? So that is the second way a single replacement reaction can happen. The last reaction we have to look at is double replacement. So double replacement reactions happen when we have 2 ionic compounds reacting. And these reactions are a little bit easier because all I need to do is switch the metals no matter what. Okay? Again, I'm using my solubility chart for these reactions. For single and double replacement reactions, see how I spelled solubility wrong because I was talking? Solubility chart gets used. So let's say, for example, I have lead to nitrate. Balancing ion charges and checking solubility charts. Reacting with potassium iodide. Balancing ion charges and checking solubility charts. All I need to do is switch my metals. My lead and my potassium switch. Now lead carries the same charge it started with, a 2+. So lead with iodide, I would need 2 iodides to balance the ion charges. And that is going to be a solid compound when I check my solubility chart. And then my potassium with my nitrate, I need only 1 of each to make the ion charges balance. Remember, again, you're either doing this in your head or looking at what ion charges they have when you write their formula to make sure the ion charges balance. Okay? Now to make this reaction balance, all I need to do, I have 2 nitrates again and only 1 nitrate. So I can put a 2 in front of my potassium nitrate, which gives me 2 potassiums. So I can put a 2 in front of my potassium iodide, which gives me 2 potassiums, and 2 iodides, which is good because there's 2 iodides in the PBI2. So that is my proper reaction. Okay? Now, this would be called a precipitate, PPT for short, because it is an insoluble product. Whenever you have an insoluble product, it is called a precipitate. The last thing we have to talk about are neutralization reactions. Now, a neutralization reaction happens between an acid and a base, but it is just a double replacement reaction, okay? My acid could be something as simple as HF, and my base could be something as simple as NaOH. Remember, acids start with hydrogen and bases end with hydroxide. So in this double replacement process, I switch my first elements, which are my metals. Remember that hydrogen acts as a metal in an acid. And the products I'm going to form, the H is going to go with the OH, which is technically water. And I'm going to make a salt, which is just a neutral ionic compound. That would be the sodium with the fluoride. Okay? So even though neutralization reactions sometimes are listed as their own category, they are still just a double replacement process where water and a neutral ionic compound are produced. Okay? I would need to balance that reaction still. You always balance reactions, but everything balances here. So you can either leave them blank or put ones in front of them. Okay? And that is it for our reactions. Thank you for watching this video.